Good afternoon all. So today we are moving to a topic called self-induction. Okay. So here we are considering a coil like this. And in this coil, a battery and a key is connected in series. Okay. So here the current, when we switch on the key, the current starts to flow in this direction. Okay. When the current flows through a coil, it gives rise to magnetic flux through the coil itself. You know that because we changed. It will behave like a magnet. So when you increase the current suddenly from 0 to a maximum value, the magnetic flux inside this coil also changes. So as the strength of the current changes, the magnetic flux changes. And here an opposing EMF is induced. That is, an induced EMF is produced in the coil itself with the changing current. Clear? And this EMF is known as self-induced EMF or back EMF. Understood? Now you know the direction of current from the battery is like this, from positive to negative. At the same time, the induced current produced in the coil will be in the opposite direction. Okay, so this is also known as back EMF. And this phenomenon is known as self-induction. Clear? Now again, when you switch off, that is when this key is opened, the current and hence the magnetic flux through the coil decreases from a maximum value to 0. So again, the induced current flows in the same direction as that of the battery current. Because again the direction changed, right? So it will be like this. At the moment when you switch off the key, the current decreases from a maximum value to 0. So the magnetic flux through the coil decreases from a maximum value to 0. And the induced current flows in the same direction as that of the battery current. Clear? So you can define self-induction as the phenomenon of production of induced EMF in a coil when a changing current passes through it. Clear? The phenomenon of production of induced EMF in a coil when a changing current passes through it. It is known as self-induction. Okay. Now, at any instant, you can see that the magnetic flux phi linked with a coil is proportional to the current I. Isn't it? As the current increases, the flux increases. So, magnetic flux is directly proportional to the current, or you can write phi is equal to L into I. Okay. This L is a constant in a given coil and is called self-inductance. Or simply you can call it as inductance. Okay. So phi equal to L into I, or you can write L equals phi by I. Correct. L equals phi by I. Okay. Now you know the relation between induced EMF and the flux is E is equal to minus d phi by dt. Okay. Minus d phi by dt, and phi from this equation it is L into I, so you can substitute that minus d by dt of Li, that is minus L into di by dt, minus L into di by dt. Clear? This is the expression for the induced EMF and the inductance. Clear? Now in this equation, if I equal to 1, okay, in the equation phi equals simple equation L into I, if I is taken as 1 ampere, you will get phi equals L, isn't it? So how can you define this inductance or self-inductance? You can say this self-inductance is numerically equal to the magnetic flux linked with the coil when a unit current flows through it. Self-inductance of a coil is numerically equal to the magnetic flux linked with the coil when a unit current flows through it. Clear? Again from this equation, E is equal to minus L into di by dt. If di by dt is taken as 1, then you can write this EMF is equal to minus L. Clear? So again one more definition you can say that self-inductance of a coil is defined as the induced EMF set up in the coil due to a unit rate of change of current through it. Okay? Self-inductance of a coil is the induced EMF set up in the coil due to a unit rate of change of current through it. From these equations you can define self-inductance. Okay. Now in this equation, from this equation you can write self-inductance L is equal to E or EMF divided by di by dt. Okay. So what about the unit of self-inductance? For E it is volt V divided by ampere per second, right? Or you will get V S A raised to minus 1. That is 1 V S A raised to minus 1 is actually called as 1 Henry. Clear? So the unit of self-inductance is Henry. Okay? SI unit of self-inductance is Henry. So self-inductance of a coil is said to be 1 Henry when there is 1 volt of induced EMF is set up in the coil when the current in it changes at the rate of 1 ampere per second. Okay, this thing you know, because to define 1 ampere, 1 joule, such things you have defined a lot. And here if you want to define it as 1 Henry, you can put this volt as 1, then ampere per second as 1. So the self-inductance of a coil is said to be 1 Henry if an induced EMF of 1 volt is set up in it when the current in it changes at the rate of 1 ampere per second, as you have seen in the equation. Okay, induced EMF is 1 volt and current changes at the rate of 1 ampere per second, then the self-inductance is 1 Henry. Also 1 Henry is 1 Weber per ampere. Weber you have seen, flux, the unit of flux. So 1 Weber per ampere is also the unit of self-inductance. Dimension of self-inductance is ml squared t raised to minus 2 a raised to minus 2. Okay, dimension of self-inductance is ml squared t raised to minus 2 a raised to minus 2. Okay, now next is we are going to derive an expression for the self-inductance of a long solenoid. Self-inductance of a long solenoid. So you have studied what is a solenoid, and it consists of large number of turns like this. Okay, so let us consider a solenoid here having a length L length is L, and the radius of the solenoid is taken as R. Okay, here we are assuming that this R is very, very small than L. And suppose this solenoid is having n number of turns per unit length. Okay. So we are considering a solenoid as it is a coil. Surely it will exhibit the phenomena of self-inductance, and here the coil is having number of turns n per unit length. Suppose if I current is flowing through the coil, suppose it is connected to a battery. Okay, I current is flowing through the coil. I is the current flowing through the coil. Then the magnetic field inside the coil is almost constant, you know, and the expression for magnetic field is B is equal to mu naught Ni. You have studied this. For toroid as well as solenoid, the same expression you are getting, B equal to mu naught Ni. Now, since there is a change in the magnetic flux linked with each turn, the flux is given as Ba. Okay, and you can write mu naught Nia. Clear? For B, mu naught Ni, so mu naught Ni into A. This A is taken as the area of cross section of the solenoid, which is pi r squared. And the magnetic flux linked with the entire solenoid is, you can write the magnetic, that is, this is for a single turn. Okay, this is the single turn expression for single turn. If we want to find the magnetic flux linked with the entire solenoid, you can write phi is equal to flux linked with each turn, flux linked with each turn into total number of turns. Flux linked with each turn into total number of turns. That is, you can write it as mu naught Nia into the total number of turns. You can find it as the number of turns per unit length into total length. That is what the total number of turns. So mu naught Nia into NL. Clear? So this expression will be like mu naught N squared. Okay, L A I. Mu naught N squared L I A. Clear? Also here, as there is a change in the magnetic flux, induced EMF will be set up inside by the coil itself. So there will be self-inductance of this long solenoid. Self-inductance is given as phi is equal to L into I. Right? L into I. So how can you write the expression for self-inductance of a long solenoid? Self-inductance of a long solenoid is given as, from this expression, L is equal to phi by I, right? So phi you know, that is mu naught N squared LAI divided by I. So it will be mu naught N squared AL. Clear? Mu naught N squared AL. Okay. Now, if total number of turns in the solenoid be capital N. Capital N is taken as the total number of turns of the solenoid. You assume like that. Then you can write small n means what? Small n is the number of turns per unit length. So, small n is equal to N by L. Isn't it? In this expression, you can put that value so that this expression will be L is equal to mu naught N squared by L squared into AL, right? So L get cancelled and the expression is mu naught N squared A divided by L. Mu naught N squared A divided by L. Clear? And if the coil is wound over a material of high relative magnetic permeability mu, like a soft iron or something, then the expression, in this expression, this will be mu naught will change to mu. Okay, so relative magnetic permeability you can add with that expression, so that this L is equal to mu r mu naught into N squared A by L. Okay. Clear for you? Mu r, mu naught n squared A by L. So this is how you are finding the expression, the expression for self-inductance of a long solenoid. Clear? So once again, we are considering a long solenoid having length L and radius R. Here we are assuming that this R is very much less than L. Okay. Now magnetic field B for a solenoid, you know the expression, it is mu naught N into I, and here induced current is set up inside the coil itself. So magnetic self-inductance you can find. Before that, we are moving to the magnetic flux, which is given by B into A. This mu naught Ni into A. A means area of cross section of the solenoid. Now flux linked with the whole solenoid, the total length of the solenoid, you can write it as the flux linked with each turn into the total number of turns. So mu 0 Nia into Nl, which is mu naught N squared Lai. Clear? So phi equal to L into I, from this L equal to phi by I, and this expression divided by I will give you the expression for self-inductance of a solenoid, that is mu naught N squared Lai by I. So I get cancelled and this is the expression. Okay. Now the small n means the total number of turns per unit length, and if you want to find small n in terms of capital N is the total number of turns. That is small n is equal to N by L, and substituting that value you will get L equal to mu naught N squared by L squared AL by L squared. This will get cancelled and final expression is mu naught N squared A by L. If you are considering any material of high relative magnetic permeability, in this expression the value of mu r also will come there. So L is equal to mu r mu naught N squared A by L. So this is the expression for the self-inductance of a long solenoid. Clear for you? So next phenomena is mutual induction. Mutual induction. So in the word itself, mutual means at least there should be two coils, right? So here I am considering two coils. The first coil like this, second coil near to the first coil. Okay. Now this second coil is connected to a galvanometer, and the first coil is connected to a battery, then a key, and then a rheostat. Let the name of the coils be P and S. So this is known as the primary coil and this is the secondary coil. Clear? When you switch on the key, current flows through the first coil, that is the primary coil. As a result, it produces a magnetic field which produces a magnetic flux through the coil S. Clear? If the current in the coil P is changed or varied, the magnetic flux linked with the coil S changes, which induces an EMF and hence a current in it, and it can be noticed with the help of the deflection in the galvanometer. Okay. Once again, we are passing current through the primary coil. As a result, magnetic field is produced, and there is when you increase the current, there is a change in the magnetic flux. So if the current in the coil P is changed, the magnetic flux linked with the coil S also changes and induces an EMF. So that induced current is produced and the galvanometer shows a deflection. Okay. Coil P is the primary coil and coil S is the secondary coil. Here actually, because of the production of current or because of passing current through the primary coil, it induces an EMF in the secondary coil. Right. That is why this phenomenon is known as mutual induction. So it can be defined as the phenomenon of producing induced EMF in one coil due to a change of current in the neighboring coil. The phenomenon of producing induced EMF in one coil due to a change of current in the neighboring coil. And this phenomenon is known as mutual induction. Okay. Now, as I told, at any instant, the magnetic flux linked with the secondary coil is proportional to current in the primary coil. If you are changing the current, means the flux also, the induced EMF produced will also vary. So you can say that this flux produced is proportional to the current. The flux is produced in the secondary coil. Okay, flux linked with the secondary coil, and current is the current in primary coil. So this constant is changed, proportionality symbol is changed by a constant known as M. So M into I, where M is the coefficient of mutual induction. Okay. So any change happening in the current I sets up an induced EMF in the secondary coil. Also, you know, EMF is equal to minus d phi by dt. Instead of phi, you can put the value, that is minus d by dt of mi. So m is the constant, di by dt. Okay, that is EMF E, induced EMF E is equal to minus m into di by dt. Now, similar to the last case, you can put I equals 1. So, this is the first equation. The first equation, if you are putting I equal to 1 ampere, phi equals m. So, how can you define? As it is the mutual inductance of two coils is numerically equal to the magnetic flux linked with one coil when a unit current passes through the other coil. As you know, here the magnetic flux linked with the secondary coil, that is the flux given here. But this I is the current in the primary coil, isn't it? Putting I equals 1, phi equals m from the first equation, and here you can define it as the mutual inductance of two coils is numerically equal to the magnetic flux linked with one coil when a unit current passes through the other coil. Okay. Also, di by dt, if you are putting 1, in this equation number 2, you can write 2 will change as E is equal to minus m, isn't it? Again, mutual inductance of two coils may be defined as the induced EMF. Mutual inductance, two definitions, okay, for two equations. Mutual inductance of two coils may be defined as the induced EMF set up in one coil and the current in the neighboring coil changes at the unit rate. Okay, mutual inductance of two coils may be defined as the induced EMF in one coil when the current in the neighboring coil changes at unit rate. Clear? So, in this way you can define the coefficient of mutual induction or mutual inductance. Now the units, again it's induction only, so the unit is Henry. So the unit of mutual inductance is Henry. Also self-inductance is Henry. So how can you define 1 Henry? Yes, 1 Henry means in this equation you can write M is equal to E divided by di by dt, isn't it? So E is in unit volt and this is ampere per second. So mutual inductance of two coils is said to be 1 Henry if an induced EMF of 1 volt is set up in the one coil when the current in the neighboring coil changes at the rate of 1 ampere per second. Okay, just a difference because current in the primary coil is the reason for the magnetic flux in the secondary coil. So in that way you have to define it. Okay, that's only the change. So once again, mutual inductance of two coils is said to be 1 Henry if an induced EMF of 1 volt set up in the first coil. This is for the first coil, induced EMF. When the current in the neighboring coil, this is for the second coil. Okay, current in the neighboring coil changes at the rate of 1 ampere per second. So in the last case, we have seen the self-inductance of solenoid, long solenoid. Now here we have to discuss the mutual inductance of two long solenoids. Okay, so next our topic is mutual inductance of two long solenoids. For this, you have to consider two long coaxial solenoids. Okay, coaxial solenoids. That means along the same axis. So this is our first solenoid. Okay, first solenoid. Let this be S1. And I1 amount of current is passing through the solenoid S1. Clear? Now the second solenoid, we can place it like this. Okay, here this is the S2 solenoid through which I2 amount of current is passing. Solenoid S2, I2 amount of current is passing. Here S2 is wound over S1. Okay, S2 solenoid is wound over S1 solenoid. So you can take the length of the solenoid as L. L is the length of each solenoid. Okay, then you can consider two radii R1 and R2, the radii of two solenoids. So for the first case, area you can write it as pi R1 square. Okay, now the area of cross section of the solenoid S1 is A. Okay, S1. And here you can take the number of turns as N1 and N2 for the two solenoids. So first what we are doing is, you can see that the solenoid S2 is wound over S1. So here we are passing a current I2 through the solenoid S2. Okay, first we are passing a current I2 through the solenoid S2. So I2 current is passed through S2. So when I2 current is passed through S2, you can see that a magnetic field is set up inside S2 due to this current, isn't it? So you can write the expression for that. The magnetic field set up in S2 due to I2. What is the expression? As general expression is B equal to mu naught Ni. Here current is I2, isn't it? And the number of turns you can take it as N2. So the expression is mu naught N2 I2. Clear? Capital N is the number of turns, total number of turns. Small n is the number of turns per unit length. Keep it in mind. Okay, small n is capital N by L. So in the expression we have small n. So this is the first expression. Clear? Now let this be equation number 1. This is the magnetic field set up in the solenoid S2. So you can write it as B2. Okay. Now the total magnetic flux set up in this inner solid S1, because you know when you pass current through the solenoid S2, actually magnetic flux is produced where? In the solenoid S1, isn't it? So the current passing through S2 will cause a change in magnetic flux in the S1. So you can write the expression for the total magnetic flux linked with S1. You know the expression, that is B A, isn't it? Flux is equal to B into A. Here B A, and also you have to note the number of turns also. Okay, listen here carefully. The magnetic flux is produced in S1 because of the magnetic field in S2. So B is B2. Understood? And the number of turns you have to mention here is with S1 only. Clear? The total magnetic flux linked with S1 is phi is equal to, or phi 1 is equal to B2 A N1. Clear? Now for B2 you have the expression, so mu naught N2 I2 A N1. Clear for you? Now listen. Mutual inductance of coil 1 with respect to coil 2 is given by M. You can write it as 1, 2. That is mutual inductance of the first coil. Okay. With respect to coil number 2. The mutual inductance of first coil is actually the flux change linked with the first coil, and it is because of the current in the secondary coil. Understood? Same as we defined. So phi 1 by I2, and the expression for phi 1 is mu naught N2 I2 A N1 divided by I2. Clear? So how does this change? Mu naught N2 A N1. I2 get cancelled. Mu naught N2 A N1. Clear for you? So here this N2 can be changed. How? N2 is what? Capital N2 by L, isn't it? So this will change to mu naught N1 N2 A by L. This N2 by L is small n2. Clear for you? Mu naught N1 N2 A by L. Clear? This is the mutual inductance of coil number 1 with respect to coil number 2. In the similar way, you can find the mutual inductance of coil number 2 with respect to coil number 1. For that, first you have to consider the magnetic field set up in S1 due to I1. That is, so magnetic field B1 due to I1 is B1 equal to, the general expression is mu naught Ni. Okay, for B1 the current is I1. So mu naught N1 I1. Small n1 is the number of turns per unit length. Small n1 is equal to capital N1 by L. The total flux linked with S2 is phi 2 is equal to B1 A N2. For B1 you can put the value mu naught N1 I1. Okay, then A and N2. Now again this N1 can be changed because it is capital N1 by L. So you substitute the value there. So mu naught N1 N2 A I1 by L. Now you want to find the mutual inductance of coil number 2 with respect to coil number 1. So phi 2 by I1, because you know the flux change in coil number 2 is because of the current passing through the primary coil. That is mu naught N1 N2 A I1 by I1 L. Okay, I1 gets cancelled. So mu naught N1 N2 A by L. So this is the same expression as we got right now for the mutual inductance of first coil with respect to the second coil. And this M12 and M21 are equal, so that you can take it as M. So M12 is equal to M21, which is equal to M. So you can write the general expression as M is equal to mu naught N1 N2 A by L. Clear? Now what is this N1? N1 is equal to small n1L and N2 is small n2L. So, mu naught n1L into n2L into A by L. Clear? So L get cancelled and final expression mu naught n1 n2 A L. Clear? A is the area. So pi r square. Clear for you? So the mutual inductance of two coils is the property of their combination. It does not matter which one of them function as the primary or the secondary, and this fact is known as reciprocity theorem. Understood? That means it does not matter which one of them function as the primary or the secondary. Only the mutual inductance of two coils is the property of their combination. Clear? This section is very important because so many times it is asked for the board exams. So study it thoroughly. And what are the factors on which mutual inductance depends? So the factors on which mutual inductance depends. First one is, as you know, it is the number of turns. So if the number of turns of the solenoids is larger the number of turns, greater will be the mutual inductance. If the number of turns is larger, mutual inductance will also increase. Second one is common cross-sectional area. Again, if the area is larger the area, larger will be the mutual inductance. Now the third is relative separation between the solenoids. Larger the distance between the solenoids, smaller will be the magnetic flux linked with the secondary coil due to the current in the primary coil. Okay. So, as you know, there are two coils, one wound over the another, and the relative separation between these two, if the distance increases, which means that the mutual inductance decreases. Okay. So, separation increases means mutual inductance decreases. Clear? And number 4 is relative orientation of the two coils. That is, the mutual inductance M is considered to be maximum when the entire flux of the primary is linked with the secondary. That is, when the primary coil completely envelops the secondary coil, we will get the maximum value for mutual inductance. Understood? And if M is minimum, means when the two coils are perpendicular to each other. The case where you are getting like this way, that is completely wound, the primary coil is completely wound over the secondary, means mutual inductance is maximum value, and if this is in such a case, means perpendicular to each other or something like that, we will get minimum value for mutual inductance. Understood? Here the value of mutual inductance is minimum. So one more factor you can say, that is about the permeability of the core material. Okay, that is the fifth factor, permeability of the core material. The core material that we are using, if it is having good permeability, relative permeability, we will get mutual inductance as a larger value. Suppose if you are using iron core or something, it is having a relative permeability, greater value, so that their mutual inductance also increases that much times. Understood? If the iron core has a relative permeability mu r, then the total value of mutual inductance will increases mu r times of the original value. Understood? So these are the factors on which mutual inductance depends. Number 1, number of turns, then common cross-sectional area, relative separation between the solenoids, then relative orientation of the two coils, and permeability of the core. Okay? So with this chapter ends here, and now we will move to the second section of this unit, that is alternating current. Okay, so that you can watch in the next video. Thank you.